fellow physicists, and welcome to another episode of Curious Conversations. Today I'm joined by an applied radio astronomer who has recently been conducting groundbreaking research into the Kessler Effect. He is also a lecturer in first-year physics at Curtin University. Welcome to the show, Dr. Paul Hancock.
Thank you. Glad to be here.
So, Paul, I mentioned in that introduction that you've been doing research into the Kessler Effect, proposed by Donald Kessler in 1978. Most recently, you're the second author on an article titled The Development of Non-Coherent Passive Radar Techniques for Space Situational Awareness with the Murchison Widefield Array. Bit of a mouthful, but well, most people have an abstract idea of the Kessler Effect from the 2013 film Gravity, with all the satellites breaking down, but we don't really understand it. So would you mind explaining what the Kessler Effect is and why it's significant?
So effectively, the Kessler Effect describes a runaway situation in which you have a lot of satellites and debris that are in orbit around the Earth. And as you add more and more satellites to the equation, the likelihood of any two objects colliding with each other is going to increase. Now, the problem is that when two objects collide with each other, they create a large cloud of debris. And so you get more space junk and more space debris, further increasing the likelihood of future collisions. So the problem is that even very small pieces of space debris, things that are only about as big, as like a centimetre or a couple of millimetres across, can cause catastrophic damage to satellites, to astronauts if they're out and about doing their thing. It can punch holes in the space station, it can break communications arrays, and it can destroy solar panels. So the Kessler Effect describes a situation in which you have so much material in a particular orbit that as soon as you have one little collision, it creates more objects, which then create further collisions, and you just get this runaway set of collisions where everything that's in that orbit will essentially just be turned into space debris. There'll just be so many of these collisions that everything gets completely wrecked. So the worry that we have at the moment is that there is so much debris in space. In fact, most of the objects that are in orbit around the Earth are actually either defunct, i.e. not working experiments and satellites, or they're just pieces of debris, rocket bodies, broken up pieces of previous satellites. So the worry at the moment is that even though we're not at that tipping point yet, thankfully, that if we don't do something to mitigate the effects of putting new things into orbit, then we're going to have to deal with the Kessler Effect eventually.
So there's enough stuff in orbit that, would you say that like something of this size, really tiny, could potentially just break down an entire satellite and that satellite?
Oh, definitely. And something like this size, this actually, it looks like a piece of plastic junk, but it has a little bit of heft to it. And so this is going to be particularly dangerous. Things that are orbiting in low Earth orbit are traveling at tens of kilometers per second. And so these very high velocities, even with such a small mass, represents a large kinetic energy, which can then, you dissipate all of that into a small part of your spacecraft. Bye-bye spacecraft.
But in detecting this space debris, you used the Murchison Widefield Array in your research to survey satellites in specifically low Earth orbit.
Mm-hmm.
According to your article, the Murchison Widefield Array is a radio interferometer with a frequency range of 70 to 300 megahertz. How is it possible that low-frequency radio waves can be used for that?
Excellent question. So normally the way that we detect things in low Earth orbit in particular is we either use optical telescopes, so we just look for the sun reflecting off satellites and space debris in low Earth orbit, or we use radar technology. So the same sort of radar that you would have at an airport or you might have on a boat or something like that. this kind of radar directed into space, you can bounce that off the satellites and pieces of space debris. So for a radar technology, you need a transmitter. Usually that transmitter is beamed in the direction that you're interested in, and you're looking at the reflected signal. The radar that we would usually use operates at a few gigahertz, which means that the wavelengths of that radiation are sort of a centimetre, maybe a couple of centimetres at most, which means that you can really focus on some of the smaller objects. People have not traditionally used low frequency radio radar, haven't even really bothered to build them, specifically for looking for space debris, partly because the wavelength's so long. So at 100 megahertz, your wavelength is about 4 meters, and so you may expect that you would only see some of the larger objects in low Earth orbit. So what we've done with the MWA is we've set up a bit of a sneaky system, which is to use a bistatic radar, which is to say that your transmission station and your receiver are not co-located, so they're physically distant from each other. And moreover, we've decided to not use our own transmitter system, but take advantage of all of the many, many transmitters all around Australia, which are transmitting in the FM band. So anybody who's listened to radio on the FM channels from 88 to 108 megahertz, that's the Australian FM broadcast band, and we have a lot of radio towers all around Australia. They're all beaming their radiation out sideways to try and hit all of the people in their cars and houses. And for some of those radio stations, the radiation will leak up into space. It will reflect off a satellite or a piece of debris, and that radiation then gets reflected back down, and we can receive that with the MWA telescope. So that's a general principle of how what we call bistatic passive radar works. So passive because we're not actually controlling the transmit power. So that's a general principle of what we're doing. This technique is using essentially every piece of the puzzle in a way that it was not intended. So the MWA telescope was designed to do astrophysics. It was designed to explore the early universe. It was designed to look for exploding stars and to look for supermassive black holes at the center of galaxies. And we've decided that all of that distant, faraway stuff is not so interesting, and that we'd prefer to look very nearby, to look at objects that are only a few hundred kilometers from us.
Because you're looking at objects that are so close, that's very easily applicable. And so how might that information actually be applied in order to mitigate or even prevent the growth of a debris belt around the Earth?
Okay, so what we have is, firstly, a whole heap of objects in low Earth orbit. And what we want to be able to do is firstly know where they all are. Okay, so for some of the objects, and this is actually only a very small fraction, some of the objects, they have onboard propulsion systems, and they're actually able to maneuver to change their orbital states. So that if there was, say, the ISS, for example, although actually it's not a good example because it's very heavy and it's hard to move, but satellites like maybe the Hubble Space Telescope, they have some very limited propulsion system on board. They can move very slowly to change their orbits. And so if we know that there's a future collision event that is possible or imminent, then we can tell these various satellite operators that they want to move their resources around. Most of the stuff that's in space is either finished with all of its propulsion, so it's run out of the gases that it uses to propel itself, or it never had any propulsion to begin with, or it's just a piece of space debris. So the strategy that we're taking at the moment is that we want to know where everything is so that we can predict collisions, and so that we can understand how close we are to potentially having a Kessler effect, a Kessler event take place. And it also means that some of the active mitigation strategies that people have developed, which is trying to deorbit and clean up essentially some of this space debris, that they know where they can put their resources to try and remove these things from space.
It's very interesting applications. But not every project using the Murchison Widefield Array has such obvious applications. Many of the projects on the Murchison Widefield Array are curiosity-based. And so what is the value of that curiosity-based research?
Well, I mean, curiosity itself is a value, is it not? So a lot of the projects that are using the MWA telescope are what we would say pure science, or some people call it blue sky research, which is the sort of research that you do, which is driven by a curiosity or a want to understand the universe, or in some cases even, I mean, some of the work that's being done with the MWA is to understand the instrument itself. So we have a whole engineering group who build and operate the telescope, and they want to understand how the telescope works. So there's a lot of different science cases for the MWA. Some of them have less direct day-to-day implications. So one of the projects that I worked on was the GLEAM survey, which is essentially a survey of the whole southern sky using the MWA telescope. We produced an amazing map of some nearly 300,000 radio galaxies. And that, to the everyday person probably isn't particularly interesting, but it does add to our general understanding of the universe. And what tends to happen is that our need for understanding of the universe, our desire to explore, drives our investment in the telescope technologies. So some of the things that we're doing with the MWA telescope are very new in terms of the technology that's being developed and demonstrated, and this is then having applications into things like mobile phone technology. So the 5G technology that you have in phones now, one of the big advancements there is that the little tiny receiver is actually now a directional receiver and sender of information. So instead of broadcasting your phone signal all around the place, hoping that it's going to hit a tower somewhere, your phone can actually know where that tower is. The tower can know where your phone is, and they can beam their radiation at each other. So you can use less power, and you can also have, essentially, it ends up meaning that you can have a higher bandwidth for your mobile data usage. So that is sort of like a less direct link between the developing the telescope that we want so that we can do the astrophysics that we need requires that we have a telescope that sits on the ground and can electronically steer itself across the sky. Those same ideas and technology can be put into our phones to help us in our everyday lives.
So do you just end up with tangential applications, like how quantum mechanics would have been applied to produce colours in phones, on phone screens and that?
Yeah, so a lot of the applications are tangential in that way. They're sort of, you're using the funding for blue sky science to build instruments, and often these projects are not just use an existing instrument to do something useful, they're developing new technologies, and the technologies will be developed for taking photos of the night sky. And in fact, that's where some of the first digital camera technology came from, was people wanting to image the sky in a very sensitive way, and not have to use chemical emulsion on glass plates and things like that. So there are many sort of knock-on effects like that occur, and then every now and then something amazing happens, and we discover relativity or the gravitational waves and things like that, which probably has a more direct link to our everyday lives.
So all of these amazing discoveries can be done using the Murchison Widefield Array, and yet it's expected to be superseded by the Square Kilometre Array in the late 2020s. What makes the SKA such a significant step up from the MWA? And what kind of impact might its observations have on radioastronomy?
So the SKA telescope, the Square Kilometre Array, is designed to be effectively two telescopes in one. There's a mid-band telescope which is operating at gigahertz frequencies, and then there's a low frequency component which is going to be operating at low frequencies, surprisingly enough. And the MWA is a precursor instrument to the SKA low, which means that a lot of the technology that we're developing for the MWA is with a forward look to say we need this technology in order for the SKA to work. So back in 2000, I think it was, the early days of the SKA, they had these grand plans of we want a telescope that can meet these science goals. And at that time, there was no technology available to build that telescope for less than, I don't know, the total economy of the Earth or something, right? So part of the SKA plan is we have these grand science goals that we want to meet. In order to meet those goals, we need to develop the technology, so hardware technology, but also software technology, data processing, workflows and things like that. These all need to be developed to make the project possible and feasible. And so the MWA is one project that is along the line of trying to demonstrate technology for the SKA. And the other thing is that the SKA, as compared to the MWA, is going to be a much larger and much more sensitive instrument. So the MWA is made up of 128 tiles out in the Murchison desert. I don't recall off the top of my head what the collecting area is, but it's nothing like a square kilometre. So the collecting area of the SKA is going to be enormous, and that means that it can have a very sensitive view of the radio sky. Not only that, the SKA is going to be much more distributed than the MWA. So the MWA has a lot of tiles that are very close to each other, which give us a low resolution view of the sky. And they have a few tiles that are maybe up to 6 kilometres apart, which gives us a slightly higher resolution view of the sky. The SKA will have stations, they're not tiles, they're stations, that will be distributed all around Western Australia and even into other states as well. So there'll be much, much longer baselines in the SKA.
And there are a few in South Africa and New Zealand as well, aren't there?
Yes, so there will be, for the low frequency, it will be in Australia, and then the mid frequency will be in South Africa. So there's that sort of split telescope design. The two parts of the instrument, you won't combine their signals together directly, but of course what we always end up doing in astronomy is we take information from the low frequency, the mid frequency, we add in a bit of optical data, UV, gamma rays, X-rays, everything that we can to try and build this complete story of the universe and of the objects that we're looking at. So yeah, so the SK will be mid-frequency radio telescope in South Africa and the low-frequency telescope in Australia. That low-frequency component will have very long baselines, which will give us a much higher resolution view. So the advantages over the MWA will mean much higher resolution and much more sensitivity. But we need the MWA, again, as a stepping stone, and this time as a scientific stepping stone along the way to the SKA, so that we can use the MWA to understand what the sky looks like at this low sensitivity, low resolution, so that we can actually calibrate the SKA telescope. So you sort of need to know what the sky looks like a little bit before you can then go out and start making images of the sky. It's a little bit of a circular process, but yeah, that's how it works.
So given the significant increase in the resources available, what kind of problems do you think that the next generation of astrophysicists will have to solve?
So astrophysicists at the moment are primarily focused on actually answering astrophysical problems. But more and more what is happening over time is that astrophysicists are having to become more data scientists. The volume of data that we are capturing, even with the MWA telescope, is terabytes per day, terabytes per hour in some cases. And so we need to have the hardware, the software, to be able to process that data. But these are instruments that we effectively built ourselves. There's no MS radio telescope or something that we can just get from Microsoft. So we have to develop these software tools, and we need astronomers with the astronomy and astrophysics knowledge to be able to say, yes, these tools are doing the right thing, but we also need people with software expertise. So one of the biggest challenges that I see at the moment is that we have a lot of amazing physicists and radio astronomers who are working on these projects, and we really vitally need more people with more computer science expertise, more coding expertise, who also know something about radio astronomy.
You lecture Physics 1 and Physics 2 at Curtin. How?
Actually, at the moment, only Physics 1.
Only Physics 1. Okay.
Sorry, should have let you know.
So how do those units and a physics degree at Curtin help students cultivate the skills like programming skills, like data management skills that you've mentioned, and prepare them for a future career?
So the physics courses, the physics curriculum that we have at Curtin, it includes not just your standard physics courses, but there are also computing courses that are built into each of the different streams of the physics major. And we've put those computing courses in there because no matter what career you will look for in the future, no matter what stream of physics that you're interested in, computing will be a vitally important skill to have. So we recognise that, and so we've embedded that into many of the curricula. Moreover, we've just starting last year, we've had an explicit high-performance computing course that we've developed for the honours level. So all the students who are doing honours at Curtin now in the physics degree are now recommended to do the HPC course, and so they'll gain skills in GPU programming, how to use and create parallel architecture programs, how to deal with large data problems, and also how to orchestrate workflows as well. So that's one of the things that we're very keen to develop for all of the students here at Curtin.
Well, that's all we've got time for this episode. So thank you for Paul. Thank you, Paul. That's interesting. That's all we've got time for this episode. So thank you, Paul, for agreeing to be here today.
It was a pleasure.
If you want to see more content like this, make sure to hit the subscribe button and ring the little bell icon. Or if you want other people to see our videos, please like, share, and comment below.
And until next time, stay curious.